Okay, so for our Kc expression, notice that the expression itself does not include water, all right? Because water is in the liquid phase. Liquid and solid, remember, if they are in a heterogeneous equilibrium, they will not be included in our Kc expression. All right, next, let's talk about temperature, all right? Our Kc and Kp, right, equilibrium constant, are only affected by temperature change, all right? Changes in concentration, pressure, and catalyst will not affect your equilibrium constant, all right? Okay, so when we consider this equilibrium, right, A plus B, you get C and D. Okay, for exothermic reactions, when we increase the temperature, all right, if the delta H, right, is less than 0. So when we increase the temperature, equilibrium will shift to the left, all right, because when it shifts to the left is towards endothermic reaction. Remember, if forward is exo, backwards will be endo, all right? So what will happen is that the Kc or Kp will actually decrease. Similarly, if we were to decrease the temperature, the effects will be the opposite, all right? Effects will be the opposite. Okay, so if let's say we will talk about an endothermic reaction, and if we increase the temperature, obviously position of equilibrium is going to shift towards the right, and then we will get more of the products, and our Kc-Kp value will actually increase. All right, position of equilibrium will shift to the left if we decrease the temperature. All right. So we now move on from the theory and the concept. We will move into calculations involving equilibrium constant. So for physical chemistry, right, remember I shared with you guys, for physical chemistry like gases, chemical equilibrium, all right, all these chapters are going to be revolving around calculation. All right, so for us to calculate, right, the very first thing that we need to do, like more concept, right, normally we would need to write down the balanced chemical equation. All right, after doing that, right, then we are going to actually write down the equilibrium constant expression. And then last of all, we need all the equilibrium concentration of all the species involved. All right, if we are not given this concentration, we can use the ice table to find them. So what's ice table? Let's take a look. Okay, so for this example, right, we are given ethanoic acid, all right, ethanol. They will mix and allowed to reach equilibrium. So the question has given to us the equations, all right, so we do not have to write that ourselves. And they have also told us, right, the mixture contains 0.67 mole of the product ester, all right, and they want us to calculate the equilibrium constant Kc for the reaction. Okay, so the analysis is this, right? Obviously the equation has been given to us, so we start from step 2, which is to write down the Kc expression. Since we are only given one equilibrium constant, we will need to use the ice table to find the rest. All right. Okay, so what is your ice table? Okay, it is actually your initial, the change, and the equilibrium. So if you see from your ice table, I, C, E. Okay, initial, change, equilibrium. So basically, I've listed down what we're given. Okay, based on the stoichiometric ratio, right, we're going to find out how much are we going to get, all right, in terms of the product. So we know that 0.67 is our equilibrium amount. So what this means is that, okay, right off the start, right, you won't have any product, right? Okay, since the amount of ester and the amount of water formed will be the same because they are in the ratio 1:1, we can also deduce that the amount of water formed is 0.67. Okay, from 0 to 0.67, what is the change? Very obviously, is going to be addition of 0.67. Okay, likewise, when we look at the reactant, if the product adds 0.67, it means that the reactant have to take away 0.67. All right, and that's exactly what we're going to put down. So 1 mole minus of the 0.67, you're going to get 0.33 for each of them. So this is how we actually do the calculation. Hopefully you're following the process. If not, just pause this video, rewind it, and then play again. All right. If necessary, you can slow down the playback speed so that you can have the time to take in the content. All right. So now we're gonna put the Kc expression. All right, and we're gonna substitute in our rho of equilibrium concentration. All right, so we just sub that in. Okay, remember this ice table, right, is in terms of moles. All right, so if we want to put it into the equilibrium expression here, right, which are all in terms of concentration, we will need to divide all of them by the volume. Okay, where did we get this volume from? Okay, here. All right, so always remember this step. Even though the volume will cancel out, we try to put it in, right? We need to try to put it in. But for you guys, I think this is a moot point because you're not going to show you're working in MCQs, right? Okay, so let's look at part B. Okay, the same equilibrium. Now we're starting with 2 moles, again in the same volume vessel. Given that the Kc is 4.12, all right, what we calculated earlier, determine the equilibrium amount of the ester. Okay, so the equilibrium amount we're not given now, we just let it be x. All right, so the initial amount of the product is actually 0 as per part A. All right, so and then obviously we're going to form X amount of water. The change is X. All right, so for reactant wise, it'll be minus X, and then equilibrium amount will be 2 minus X. All right, so we'll plug all this in. We'll plug all this in, this whole row, and then once again, we're going to solve for X because now we've got the Kc, right? We can solve for X. So we realize that our X is 1.34. Okay, so to get the equilibrium amount of the acid, is actually just X. All right, then what's the percentage yield? By right, we're supposed to get 2, right? Okay, so if we got 1.34, our percentage yield is only 67.